Okay, thank you very much for that. So today I'm going to talk about actually how we design. I'm actually going to talk about design. How do we physically design alongside computers? This is, of course, Sketchpad by Evan Sutherland, thought of as one of the first sort of computer-aided design process. Sort of showed that computer graphics could be used both artistically and technically. Is the way we design, physically design, that far from this? And of course, many years ago, that wasn't how things were designed. Take, for example, ship design. The complexity of ships and things like this was such that we didn't have the means to produce CAD drawings and thus didn't design with CAD. Instead, there was different methods. The method here was more procedural. They would set out the ribs, say, a bit like control points, and then they would take a big, long plank of wood and then wrap it around those ribs. And that would generate the shape. So not much CAD there. As a side note, those long planks of woods were termed splines. So any of you 3D modeling enthusiasts, that's the derivation of that term. And so it was really constraints and technology that sort of resulted in peculiar ways of design as well. So these two people are designing the wing of a plane. They're doing it at a one-to-one scale. The challenge is that they couldn't quite do this in the shop, so they do it in the loft of the thing. And that's really quite challenging, and they came up with this solution. And again, any of you 3D modelers out there, it's the derivation of the word lofting a surface. And it really wasn't until recent sort of that car design revolution, Pierre Bézier de Castillal, that we see the kinds of design techniques that we are kind of common today. That is to say, sort of formulaic descriptions of complex designs with parameters that are manipulatable for, say, design optimization. And of course, these things were happening in that space, were sort of neatly timed with the innovations of people like this, Ada Lovelace, the sort of general purpose computer, so thinking algorithmically. So this perfectly benefited those kinds of car designs where Bézier was spending 3 weeks to do the calc. It brought it down to minutes in these sort of parametric models. How much then has changed today? And so I kind of will start with sort of saying, how would one, say, go about designing a chair? And what you're really interested in with this chair, performatively, is the comfort of that chair. You might go about modeling it, let's say. You might conceive of it in your head, the idea, the concept, for the chair, and then you would model it. So, you may draw a section of the chair, and you might extrude it along its width, let's say. And we'll be able to test it after conceiving of it and modeling it for comfort, for the performative elements of it. You may want to get slightly cleverer, and you may want to sort of encode that logic into a computer, into a model, and then parameterize some of those variables, let's say the length and the width. And that meant that you could amend the length, amend the width, and then you could test for comfort. You could start to optimize in that manner. So you could amend it, test, amend it, test. And this is something that we're quite common today, where you would have something that is a parametric model. That is to say, there are parameters and variables of which you change, a set logic, and then a way as an output to test what you've created. What this means is you can create loads and loads of these chairs, and you can try and get the best comfort performance that you could possibly get. So you've conceived of this, and then you're trying to measure it. The challenge is that this chair that you've kind of designed will sort of never look like that, for instance. Or it won't look like that, or that. And the important thing is here, though, is they say this chair could be performing a lot better for comfort. We could even scale this up to say, just for instance, a master plan. Imagine doing this the same thing for a master plan. You may parameterize a model, a logic that you create. You may have length, width, positions of urban blocks. But what we often get is something like this. And this is great. And we can even try to optimize this for distance to amenities, carbon footprint, green space. However, that model will never really produce something like that. again, what's important here, this is a sort of an emergent vernacular, is that this might be performing far better. So what's a sort of another method, let's say? Well, instead of kind of going left to right, what we could do is go from right to left and start with the performative criteria. And then instead of fixing a logic that we've conceived in our heads, we might want to construct a grammar or a language for the computer to permeate in, and in its own way, create the logic. So I thought I'd quickly share some examples at Arup of ways to get the computer to do more. So the first way, conceptually, is super easy, and that's to remove the error and to build on collective learning with computers. So Arup is 14,000 plus extraordinarily talented designers, engineers, consultants, and there is a distributed culture of innovation. So what that means is that a lot of us are making similar innovative calculations and tools on many, many pieces of work and many, many projects. And really one thing that we tell ourselves a lot of time with this challenge is if only Arup knew what Arup knows. It's a real challenge. So every time we want to automate something, we have to choose the automation environment. We have to choose the programming language. We have to find existing code, decide how we store the data. And many, many talented Arupians do this. The thing is that this is a lot of effort, and we wanted to consolidate that effort. And again, remove the error, because this is a lot of repetition. So what we did is we've created a cloud-based integrated design automation platform that makes automated workflows available to all projects. And we call this the Total Design Automation Platform at Arup. And this really takes advantage of our distributed culture of innovation across Arup and connect the localized pieces of innovation. So just to give you an idea of how it's gone, design check, which is the calculation element of the Total Design Automation Platform, in the last 12 months, Arup have performed 2 million calcs in it. So instead of 2 million separate calcs by separate people, we're using the same calculation, centralizing that, massively minimizing the error, whilst also enabling data capture. So the next element I wanted to talk to you about really with computers is another easy concept, which is authorship. So this is a chess game, two players playing chess, and they play within the game. And my real question really here to you is, who is the sort of author of the chess game? Is it the chess players that are playing? Or is it the computer programmer that has written the rules for that chess game? It's kind of a bit like who is the author of a termite mound, and I always like to make that sort of reflection. Because BIM models today are much like termite mounds, multiple authors. Now, interestingly, when it comes to design specifically, the author of the chess computer program has a huge impact on the design of the game being played. The chess players can't make a drafts move. So just an example of what I mean by this in real life, and this kind of thinking. At Arup, we were asked to solve this issue for La Liga, which is the Spanish football league. I don't know if any of you can make out any of the players here, sort of very famous players here. It's pretty tricky, and that's the problem. One of the predominant reasons is the sun's location, the sun's position, as well as the brightness and exposure, not to mention the fact that over the 90 plus minutes, the sun will be moving. So to solve this issue, instead of providing La Liga with some lighting solutions for certain events, what we decided to give them was the chess computer, essentially. So what I mean by that is we provided them with an application with every single one of their stadia in, and gave them the ability themselves to choose which time of day for the next 10 years that they wanted to analyze. The app then, they were able to place cameras, and actually they were the ones designing the camera locations best for their exposure. And we gave them things such as like illuminance within the shadows and illuminance within the sun, which enabled them to even predict what type of f-stop, if you're a camera person, that they'd choose exposure into the camera. Next, I guess, is getting the computer to be truly generative, is sort of getting the computer to be more like an artisan when designing. Now, the artisan, it doesn't really do a full search of the design solution space immediately. It's a lot more about touch, feel, and sort of meanders according to sort of the previous movement to produce something, creativity. So what I mean by this, just to stick with Stadia, instead of daylight, I'm going to choose artificial light. One of the things that we do is design the locations of artificial lighting to optimize uniformity on the field of play. Now, this lighting design is extremely complex. There are hundreds of lighting positions, hundreds of lighting directions, and the uniformity is incredibly difficult to get in multiple planes. Now, we could apply some traditional global optimization techniques. We take a load of lights and we try to optimize the locations for that uniformity, which is perfectly legitimate. The challenge is here, though, that the design space, the solution space, is enormous. So we'll be there for a very long time. And you could even, say, apply some machine learning methods to predict the outcome. Again, you'd need a big data set. So instead of the global optimization techniques, we've taken a little bit of a different tack, really, in terms of approach. We've kind of tried to copy how the lighting designer usually does it. Now, the lighting designer will place a few lights, and then he'll place the next light, and then that person will place the next light, and that person, well, I get that, will continue to do this. And this is kind of somewhat more artisanal. So, lost that. There we go. So instead of what you see on the left, which is a sort of traditional global optimization technique that's going to take forever and a day for us, what we did is we encoded the logic into the computer about what it's going to do next with its next lighting, according to what it sees previously. And what we actually found in this case is the uniformity levels are extremely, extremely good, and we're not sort of iterating over and over again. So we're encoding design logic into the computer in more of an artisanal sort of sense. For me, this is what generative design is. We're getting the computer to help generate using artisanal, traditional techniques. And of course, because of digital fabrication and the sort of emerging file to factory kind of paradigm, we don't necessarily need to shy away now from complexity going to rationalization, because of the things on the right here. So going towards a performative way of designing, bringing those performances first instead of conceiving, then measuring, we don't have to do that. And, so something that I could personally envisage on the left here, I certainly couldn't envisage on the right. We've got the computer designing the stresses and looking at the stresses, the geometry of the stresses. We're actually able to take that all the way through to the final design. So the guys here, Arup, helped MX3D design this, and this, of course, is in Amsterdam today. And then finally, not being afraid to quantify. We've been measuring experience forever. Take, for example, acoustic data. We don't design today something that we think may be loud. We're actually able to quantify decibels. We're able to quantify reverberation. Not only that, we're actually able to accurately and importantly in a calibrated manner play it back to ourselves before it's even designed. And in Arup, we've been doing this for many years with something called Sound Lab, the acousticians. But we've sort of now taken it further, really, and sort of tried to introduce as a calibrated quantitative measure of the experience of this building as we possibly can. So instead of, say, data visualization, we really perceive it as data perceptualization, all the senses coming together in a shared way. So there is music to the next one, I believe, but I just wanted to show you one of our most recent facilities that we have. You can go and see it in London if you're interested, the Arup Experience Lab. And this is really trying to calibrate an experience before it's even been made. So I hope this works. So what it is essentially is a facility that we're really trying to tune, and we have things such as about 28 speakers calibrating the acoustic playback. We have a two projectors that are firing at different rates into your eyes to give you that 3D effect. But what we're interested in really is the accuracy that we can play back. It's a shared experience, so you're not necessarily inhibited by VR goggles, say. The sort of obsession I'm making about accuracy, just to give you an example of what I mean, here's an example where we're using Unreal, and we are taking our smoke computational fluid dynamics simulations and we're bringing them into real time, into a real-time engine. This is the visibility data, so each sort of data point or voxel has a visibility value like, let's say, 2 meters. And what we're interested in is when it says 2 meters from the CFD, we want it to show that you can only see 2 meters. So it's really trying to calibrate that experience. And bringing it into the 3D, obviously, into that shared space means that other people can experience it. So say a child, what is it like when we design, when we run those smoke simulations, what's it like for a child to be in that space that we might not necessarily be able to do? So just to conclude, really, for what I imagine truly generative design is, it's really sort of removing common error through the automation done, questioning and challenging authorship in design as computational designers, and then applying these novel, more artisan-like generative algorithms to complex problems, and then sort of finally not really shying away from the complexity and the data of the experience of the built environment. So I think there's some really great opportunities there for computational designers. So yeah, thank you.
So we have a few minutes for Q&A. Does anybody have any questions for Conor? We've got a full audience. This is great. Thoughts and questions? Okay, go ahead here.
Yeah. How do you balance having a highly optimized, almost bespoke design with building something that's maybe with standardizing a design? So you're having something repeatable that might not be optimized versus something that's highly optimized but might not work in every situation.
I can answer in here, can't I? Yeah. Very good point. Yes. On a side note, I think as designers that are more and more experienced with computers, they're hopefully going to be more artisanal type computational designers. That is sort of using code in a bespoke manner versus the automation way, the scalability way. But it's absolutely a lot of the time you might see a sort of protocol created, a sort of standardization way, standardized sort of logic. Interestingly, with those, the variability is really key. So how much variability is in that logic? A lot of the time when you see standardizations, it might not necessarily be as much variability as it might envisage.
Good question. Are you rolling your own tools to do this? Do you have your own user interface, own protocols for generating these types of artisanal experiences?
You mean externally?
Yes, yeah.
Yes, yes, it's a good question, because there is an approach, which is that artisanal, bespoke approach. And we have internal tools that we do that, and an ecosystem. We also just take advantage of, a lot of that work was, for example, with Rhino Grasshopper, proprietary tools that are extraordinarily useful. We're just maybe applying them in a different way than it might be traditionally used. So the tools are out there. What's interesting is the approach to them, I think.
Wonderful, thank you. Other questions? Hang on a second.
Thank you. Well, first of all, congratulations, amazing presentation, and let me tell you who I am, so you understand before I ask the question. So I work for Bentley Systems. We are a software development company. So I think looking at what you were presenting, that reminded me there is one thing that we always try to avoid as we develop software, that is the bias of the developer, right? How we perceive that is the right thing to happen. And I'm sure you guys have heard about it around AI, ML, and how we are kind of designing the new tools of the future. But how do you bring diversity into analyzing those different scenarios that you're trying to design for? And I think you mentioned a few examples, but do you have kind of like internal protocols or workflows within Arup to make sure that you are testing the scenarios from different perspectives and different personas in that story?
Yeah, I think that's actually quite a good point in the sense that there can be a disconnect between, let's call them the software engineer, the computational designer, and the person that's really making the gestures of design. So at Arup, we really try to integrate. I mean, if you are a computational designer in Arup, you can sit anywhere. So we have a very distributed sort of system for that, which I think is really, really powerful, because you get a landscape architect, let's say, who might use a different medium next to someone that uses Bentley, let's say. But it's a very good point. Yeah, that disconnect is something that we need to keep as close together as possible.
Wonderful. I think we've got time for one more question. Okay, over here.
Hi there, Andy McNeil. That's Andy from McNeil. You mentioned Rhino and Grasshopper. Are you using compute? And if you, depending on your answer, I have a follow-up question.
Sorry, the last.
Depending on your answer, I have a follow-up question.
So you mean Rhino Compute?
Yeah.
Yeah. We do use Rhino Compute. We also have Arup Compute, which is sort of using Rhino Compute, as I understand. Yeah, but
Yeah. So basically, my follow-up question is, how is that working out for you?
yeah. Goodness. So I showed you Total Design Automation platform. We're using Rhino Compute within that. So gaining, I think one thing as we develop these is the interaction with Rhino Compute as the person that's using it is really quite key. So we have variable outcomes from using it from someone that might be slightly savvier to understanding a REST API versus someone that is savvier with Grasshopper boxes, let's say. So it's variable, I think, so far, yeah, to be honest.
Okay. Good.
Wonderful. Let's give Conor a round of applause. Thank you.